All right, thank you guys. Thanks everyone for being here. I understand this is the last session of the day and of the conference, so I thank you for your patience. Let's see. The next one will be, I can figure out how to use this. OK, so I'm going to talk today about a type of computation that I think has been a little bit overlooked in the quantum world. So this is something analog quantum devices are really naturally good at, and this is analog quantum computation. And this is particularly useful for quantum simulation because quantum systems are inherently analog. So I'm the CEO of Harmoniqs. We're actually an optimal control company based out of the United States. And I would love to talk more about this afterwards. But I'm going to talk today about kind of the inherent problem and a vision for the future that we see. So quantum systems are inherently analog devices. And what this means is that these things live in continuous superpositions, and we manipulate them by shining basically lasers or something continuous at them and driving them in a way. So what this looks like, and this is a cartoon that represents a lot of systems, where most systems represent an atom in some sense, whether it's a real atom or whether it's an atom that we virtually create. And we usually do this by we shine some control signal at the atom and we rotate it in some way. We package these pulses into gates. So this is what a gate, if you do an X gate or anything digital on a quantum computer, you're actually under the hardware doing a gate. You're doing a continuous operation that does some specific discrete operation on the qubit. So what we do is we control all of these atoms, or all these elements, all these qubits individually, and we shine a lot of things in, and this could be a lot of control lines or lasers, and we do these discrete gates on each atom. And one problem for scaling these devices is that the number of control lines, the number of control signals you have to send into these devices scales with the number of qubits, which we see as a problem, and this is a problem pretty much every platform faces. So what we show in this work that I'm about to get to is that you can actually get away with shining a single laser, or basically controlling every qubit in synchrony. And you can actually get interesting things to happen by doing this, which is a little unintuitive. And we actually have a mathematical proof in the paper that I'll get to where we prove that this is the case for certain classes of systems, particularly those at QuEra and Pasqal, these types of neutral atom systems. So I'm in France, so I have to quote Antoine de Saint-Exupéry, who said, "It seems that perfection is attained not when there's nothing more to add, but when there's nothing more to take away." And I think as we scale devices, we really need to take in mind the analog nature of these devices and think about how do we scale them by leveraging the nature of them. And it comes down to how do you drive a quantum system? Like, how do you get it to actually do these things? So I'm coming at this from a background in robotics. My lab actually does all kinds of robotic control techniques, and generally robotics might be landing a rocket on a barge. And this is a very complicated task that a lot of very interesting control algorithms were developed to solve, and we can actually do this today. And it looks really cool if anyone's seen the videos. So my lab is based at Carnegie Mellon, and we spun out of there, and we work on all kinds of things: satellites, quadrupeds, autonomous driving, drones. We do all of these things, and we control them in really interesting ways. So we're leveraging these same control algorithms to design these types of analog pulses to control quantum systems at Harmoniqs. So I should mention, again, Harmoniqs is our startup, and we are the ones who worked on this project with Harvard. So when you do this, just like in the classical robotics setting, you model your system in some ways. You model your system, you model your array of atoms, and you get this quantum computer to simulate it. And we believe if you can simulate it, you can control it. And we have really good simulators for quantum computers, and that's one of the reasons we want to leverage them. Even relative to robotics, the simulators are infinitely better than some of these robotic simulators. And I could get into that if anyone wants to ping me afterwards about that. So in this case study, I want to highlight some work we did with Harvard. So this is a paper we recently put out on Archive titled "Universal Dynamics with Globally Controlled Analog Globally Controlled Analog Quantum Simulators." So this is work that was done at Harvard, UChicago, Carnegie Mellon, and Harmoniqs. And we did this on a QuEra device, the QuEra Aquila device. So the problem boils down to we have a neutral atom array, and we want to encode some Hamiltonian into it. This is some way to describe a quantum system. So we encode this Hamiltonian that is not a native Hamiltonian of the device, and we're able to actually solve for a signal of control pulses. So we can see that this system basically involved a line of atoms, so a chain of atoms, and we want them to all do something interesting by shining the same laser at all of them. And this has a number of constraints that you need to actually account for, which is where we came in, is you need to design your control signal to deal with the way the lasers turn on and turn off. They have a certain ramp-up speed. They have certain control limits. They have a finite resolution. So all of these constraints boil into the control problem to get this to happen. So we model all of this. We're able to simulate it, and then we're able to control it, and we're able to actually design pulses that look like this. So we're able to design a family of pulses that does an interesting simulation of a different quantum system. So we're able to kind of design pulses that simulate up to different timescales how a quantum system that we did not have on this device will evolve. And we're able to do this in an efficient manner. So here are some experimental results, and this is mainly for people on YouTube to potentially pause at and look at, but in brief, if you look at the top plot across, you can see for different atoms, the blue diamonds and the red X's represent the simulation and experiment respectively, and they match up rather well. Same on the bottom, we can see that the theory and experiment match up rather well. And this is just some preliminary hardware results. There's a lot more we're going to do to refine these results. But it's an exciting hardware demonstration that and I'll quote from the paper, "This is the first realization of effective three-body interactions with Rydberg atoms outside the blockade regime, going beyond the native two-body interactions." So this is an interesting, maybe niche quantum system that we were able to globally control and get something interesting out of it that was not previously thought potentially possible. Going beyond this is really where we want to explore more. So we envision like a lot of different possibilities. So I've talked to some people at QuEra, and we've talked to people at Pascal, and there's a lot of potential infrastructure to leverage the analogicity of these devices to simulate Hamiltonians and quantum systems that aren't natively in the system dynamics. So we're thinking molecules. Maybe you have some quantum circuit that you can compress certain chunks of it into pulses to run faster and more efficiently, more accuracy with higher fidelities, and bring down computation times and do more interesting things, leveraging the inherent nature of these devices. So that's what Harmoniqs kind of envisions the future to be like, and we work on all kinds of different systems. And we really, to quote another French author, Simone de Beauvoir, technologies are ways of a commandeering nature. The sky belongs to those who know how to fly, and the sea belongs to those who know how to swim and navigate. So we really think by knowing how to simulate, knowing how to control these devices at their level, we can do cool things in the future. So I want to thank everyone for coming and sitting through this last talk, and thank everyone at my lab, at Carnegie Mellon, and the Rex lab, the people at UChicago, all the people at Harvard who made this possible and ran this stuff on hardware, the Unitary Foundation, Harmoniqs, and Piccolo. So if you want to check out any of these links, please do. And please come to talk to me afterwards. In summary, so I just want to highlight again, quantum systems are analog devices, and they have to be driven. Even if you abstract this away into gates, still, you're sending continuous pulses under the hood to these things. Interestingly, global control can be universal. So this is an interesting thing, and I think on a smaller level, packaging more computation into basically boxes of optimal control pulses is a potential way to get more out of these systems in the near term. And crucially to making this happen is some of the AI robotic control methods that are being developed in other fields, like specifically robotics, that I think have not been brought over to the quantum domain yet, and that's what we're trying to do. So I'll end it there and say thank you, and if there are any questions, I'll be happy to take them.